Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss de Moivre's theorem and some questions related to de Moivre's theorem. Let's begin. Statement of de Moivre's theorem: if n is an integer that is either positive or negative, then cos theta plus I sin theta to the power n is equal to cos of n theta plus I sin n theta. That power is multiplied to that of angle. Also, if n is any rational number, then one of the value of that expansion cos theta plus I sin theta to the power n is cos theta plus I sin theta. If n is any rational number, then cos theta plus I sin theta is one of the value of that particular expansion. We have to prove the de Moivre's theorem. De Moivre's theorem can be proved in two different ways. One is by exponential method and another one is by induction method. Two methods basically we use to prove de Moivre's theorem. First, method 1. By exponential method. How to prove de Moivre's theorem by using exponential method? We know that e to the power I theta is equal to cos theta plus I sin theta. That is the Euler's formula. We take nth power on both sides. E to the power I theta to the power n is equal to cos theta plus I sin theta to the power n. Then that n is multiplied, that is e to the power I n theta is equal to that particular term. Now we expand e to the power I n theta. As we know by using Euler's formula, e to the power I theta is equal to cos theta plus I sin theta. Next, e to the power I n theta, that will be the angle. It will be cos n theta plus I sin n theta. Now we show that the expansion of cos theta plus I sin theta to the power n is equal to cos n theta plus I sin n theta. If n is a fraction, then we can say cos n theta plus I sin n theta is one of the value of that particular expansion. In this way we prove that de Moivre's theorem. Now another method, that is induction method, basically used to prove de Moivre's theorem. It is method number 2. It has three possible cases that depend upon if n is positive integer, if n is negative integer, or we can say if n is a fraction. Accordingly, we prove that particular de Moivre's theorem. Case number 1, when n is a positive integer, first we generally multiply cos theta plus I sin cos theta 1 plus I sin theta 1 to cos theta 2 plus I sin theta 2, general multiplication, that term to this, that term to that. So the multiplication results will be cos theta 1 cos theta 2 plus I square sin theta 1 sin theta 2 plus I sin theta 1 cos theta 2 plus I sin theta 2 cos theta 1. Here I square is equal to minus 1. So cos theta 1 into cos theta 2 minus sin theta 1 into sin theta 2. Here we take I as common. So in that bracket we have sin theta 1 cos theta 2 plus sin theta 2 cos theta 1. Look at that particular expression. It is in the form of cos A cos B minus sin A sin B, that is cos of A plus B. So that is cos of theta 1 plus theta 2. Again inside that bracket we have sin A cos B plus cos A sin B, that results sin of A plus B. So, sin of theta 1 plus theta 2. Again, similarly, we can prove that if I add another term, that is cos theta 3 plus I sin theta 3 to that equations, then it will be results as cos of theta 1 plus theta 2 plus theta 3 plus I sin of theta 1 plus theta 2 plus theta 3. In similar manner, we proceeding up to n number of terms. So, we write it as adding n number of terms multiplied with each other, results again in that of angle we add n number of terms, and inside that angle also introduce n number of terms. Let me put these angles as theta 1 is equal to theta 2 is equal to theta 3 is equal to theta n as theta. So, that equation changed cos theta plus I sin theta into cos theta plus I sin theta up to n number of terms, again here cos of theta plus theta up to n terms plus I sin theta plus theta up to n terms. So, the multiplication of cos theta plus I sin theta up to n number of terms results cos theta plus I sin theta to the power n, which is equal to cos n theta plus I sin n theta. Here theta added as n number of terms, so it results n theta. Again theta added n number of terms, so it results n theta. In this manner, cos theta plus I sin theta to the power n is equal to cos n theta plus I sin n theta is proved for n as a positive integer. Next, case number 2, when n is a negative integer, then how we prove de Moivre's theorem? Let me prefer n is equal to minus m, where m is positive integer. So, that expansion will be cos theta plus I sin theta to the power n is equal to cos theta plus I sin theta to the power minus m. In place of n we substitute minus m. So, it can be written as 1 divided by cos theta plus I sin theta to the power m. Now, we can expand it by using case number 1 as cos theta plus I sin theta to the power n is equal to cos n theta plus I sin n theta, that n is multiplied to that of angle. Here same concept, that m is multiplied to that of angle. So, we have 1 divided by cos m theta plus I sin m theta. Now, we multiply cos m theta minus I sin m theta, its conjugate, both numerator and denominator part. So, cos m theta minus I sin m theta, as it is the conjugate of that particular term, is multiplied on numerator and denominator. We have, in case of denominator, a plus b whole into a minus b, that is a square minus b square. So, it results cos square m theta minus I square sin square m theta. Since I square is equal to minus 1, so minus minus plus, so plus sin square m theta. So, cos square m theta plus sin square m theta, it results 1. Therefore, that term changes to cos m theta minus I sin m theta. Now, we just introduce negative here, as cos of minus m theta is equal to cos m theta plus sin of minus m theta is equal to minus sin theta. So, minus minus plus, that transferred to this equation. So, we can write negative angle introduced here. Now, minus m as replaced by n, as we prefer, n is equal to minus m. Therefore, in place of m we substitute, in place of minus m we substitute n. We have cos theta plus I sin theta to the power n is equal to cos n theta plus I sin n theta. Again, that theorem is true for negative integers, as we prefer n as negative integer. Next case, when n is a fraction, let me take n is a proper fraction, that is in the form of p by q, where p and q both are integers and q is a positive integer and p is any integer, as it may be positive or negative. Now we can prove it. So we write it as cos theta by q plus I sin theta by q to the power q is equal to, that power is multiplied to that of angle. So it will be cos q into theta by q plus I sin q into theta by q, as we use case number 1 as we studied. So q cancel out, so it will be cos theta plus I sin theta. Just rearranging that equation as cos theta plus I sin theta is equal to cos theta by q plus I sin theta by q to the power q. Now taking qth root on both sides, so it has 1 by q, again its power 1 by q into q, so q cancel out. Again taking pth power, so cos theta plus I sin theta to the power p by q, here again pth power to the power p, so that p is multiplied to that of angle term. So we have cos theta plus I sin theta to the power p by q is equal to, that p is multiplied as we use the case number 1 condition. So cos p into theta by q plus I sin p into theta by q, so p by q as we prefer here, p by q is equal to n. In place of p by q we substitute n. So cos theta plus I sin theta to the power n is equal to cos n theta plus I sin n theta. Here n is a proper fraction. So in this way, by taking n as a positive integer, n as a negative integer, and n is a fraction, we prove that de Moivre's theorem as cos theta plus I sin theta to the power n is equal to cos n theta plus I sin n theta. So here the proof of de Moivre's theorem by using two methods. First method by exponential method, it is the proof. Next by using induction method, we prove that particular de Moivre's theorem. That de Moivre's theorem is very helpful to us to solve various types of questions related to complex numbers. Now we have two questions. Now we can solve these two questions by using de Moivre's theorem. Question number 1, express it in x plus y form, as that particular question is given as cos theta plus I sin theta to the power 4th divided by sin theta plus I cos theta to the power 5th. Now we convert it in form of x plus y. Now we prepare the solution. As we know, cos theta plus I sin theta to the power n, by using de Moivre's theorem we have that angle, that power is multiplied with that of angle. So cos n theta plus I sin n theta. Therefore the term cos theta plus I sin theta to the power 4 can be written as cos 4 theta plus I sin 4 theta. That power is multiplied inside that of angle. Next we have to evaluate that term. Also sin theta plus I cos theta to the power fifth. We have to convert it in the form of cos theta plus I sin theta form. Therefore, I just multiply I here, iota here. We know iota is an operator also when it is multiplied to a particular complex number, then it is changed. So, if I multiply iota here, so it will be written as cos theta plus cos theta minus I sin theta to the power fifth. In place of cos theta sin theta plus I cos theta, I just replace by taking I or multiplying I here, that transform to that term. So, we have I cos theta, again I square is equal to minus 1 minus plus, that is sin theta. No such change will be there. Now, I to the power fifth cos theta minus I sin theta to the power fifth. I to the power fifth can be written as I to the power fourth into I. So, cos theta minus I sin theta to the power fifth. We know I to the power fourth is equal to 1, even power of I is equal to 1. I cos theta minus I sin theta to the power fifth. Using de Moiver's theorem here also. So, the power is multiplied to that of angle. You have I cos 5 theta minus I sin 5 theta. We have I is multiplied to that equation, or just write that much. Now, we can evaluate that particular term in the form of x plus iy. Therefore, we have to evaluate cos theta plus I sin theta to the power fourth divided by sin theta plus I cos theta to the power fifth. In place of that one, I write cos 4 theta plus I sin 4 theta divided by, for that one I write I cos 5 theta minus I sin 5 theta. Now, we solve it as reverse way, that can be written as cos theta plus I sin theta to the power fourth divided by I cos 5 cos theta minus I sin theta to the power fifth. Okay, is equal to, that is e to the power I theta. So, e to the power I theta to the power fourth divided by I into e to the power minus I theta divided by, e to the power minus I theta to the power fifth. Again multiply and divide I in numerator and denominator. So, it will be I divided by I square, 4 is multiplied. So, e to the power I 4 theta divided by e to the power minus I 5 theta. So it will be I square is equal to minus 1. So minus I e to the power I 4 theta into e to the power plus I 5 theta. Now minus I e to the power I 4 theta plus I 5 theta, that results minus I e to the power I 9 theta. Now that exponential term can be written in terms of cos theta and sin theta. Minus I cos 9 theta plus I sin 9 theta. Now I is multiplied to that of bracket term, it will be minus I square plus 1. So sin 9 theta minus I cos 9 theta. So that particular term we now write in terms of x plus iy format. Here a question struck to your mind. As you know, cos theta plus I sin theta to the power n is equal to cos n theta plus I sin n theta, but here is a negative one. How is it possible? So a note you have to remember. Here I just write a note to clarify you. Note you have to remember, when cos theta minus I sin theta to the power n, now we introduce the negative angle, so that can be written as cos of minus theta as cos theta plus I sin of minus theta as sin of minus theta is equal to minus sin theta to the power n is equal to, again using de Moivre's theorem also, that power is multiplied to that of angle. We have cos minus n theta plus I sin minus n theta. Cos of minus angle is equal to cos theta. So cos n theta, here negative angle of sin, that is minus I sin n theta. So we have cos theta minus I sin theta to the power n is equal to cos n theta minus I sin n theta. Generally that power is multiplied within that of angle. Next, same thing, when we refer 1 divided by cos theta plus I sin theta, that can be written as cos theta plus I sin theta to the power minus 1, that negative power also multiplied within this. So we have cos of minus 1 theta plus I sin of minus 1 theta. So cos of minus theta, that is cos theta, sin of minus theta, that is minus sin theta, I sin theta. That is 1 divided by cos theta plus I sin theta can be written as cos theta minus I sin theta. These two are the important notes you have to remember when apply de Moivre's theorem. That important theorem is also useful when we solve that question here. Now another question we have to solve by using de Moivre's theorem. If n is a positive integer, then we have to prove that 1 plus I to the power n plus 1 minus I to the power n is equal to 2 to the power n plus 2 divided by 2 into cos n pi by 4. solution 1 plus I. When we write it as x plus iy format, here x is equal to 1, y is equal to 1, therefore r is equal to x square plus y square under root, that is 1 square plus 1 square under root, it is under root 2, and tan of that angle, tan of theta is equal to y by x, that is 1 by 1, or theta is equal to tan inverse 1, that is tan inverse tan pi by 4 value is 1, so we have theta is equal to pi by 4. So in polar form, this is in Cartesian form. So in polar form, 1 plus I is written as r into e to the power I theta. These values are put here. So r is equal to root 2 e to the power I theta is equal to pi by 4, or 1 plus I is equal to root 2 e to the power something. Now expand as cos theta plus I sin theta form. We have cos pi by 4 plus I sin pi by 4. Similarly, 1 minus I to the 1 minus I can be expanded in that form. Similarly, 1 minus I is written as root 2 cos pi by 4 minus I sin pi by 4. Now we have to evaluate that expression. Therefore, 1 plus I to the power n plus 1 minus I to the power n. For that purpose, we use root 2 cos pi by 4 plus I sin pi by 4 multiplied with root 2 cos pi by 4 minus I sin pi by 4. To the power n, here to the power n. From these two terms, root 2 to the power n here addition, not multiplication, here addition. So root 2 to the power n as common. In that of bracket term, we have cos pi by 4 plus I sin pi by 4 to the power n. Again, using de Moivr's theorem, we write it as cos n pi by 4 plus I sin n pi by 4. Again here cos n pi by 4 minus I sin n pi by 4 plus minus cancelled out, root 2 to the power n, here 2 times of cos n pi by 4. Now this is 2 to the power n by 2, as root 2 is equal to 2 to the power half. So half into n, that is n by 2 into 2 cos n pi by 4. So 2 to the power n by 2, 2 to the power 1, that will be 2 to the power n by 2 plus 1 into cos n pi by 4, which is equal to 2 to the power, taking the LCM, we have n plus 2 divided by 2 into cos n pi by 4, as it is shown as. We have to prove that one. So here it is proved. So with the help of this video lecture, we understand de Moivr's theorem and its proof by using exponential method and by using induction method. Important notes related to de Moivre's theorem and problems we can solve by using de Moivre's theorem. This is problem number 1. Next, problem number 2. So, with this useful and informative notes, let me wind up this session. Thank you.